Welcome to the course Introduction to Algorithm. My name is Sourav Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course on algorithm. So, in this lecture we will cover shortest path. So, this is the shortest path one. We will discuss, we will start with the what do you mean by shortest path in a graph between two vertices u and v, and then we will discuss, in this lecture we will discuss two algorithms, namely Dijkstra's algorithm and Bellman-Foote algorithm to find the shortest path from a given vertex to a all other vertices, weight of the shortest path. So, that two algorithm we will discuss. So, let us start the lecture. Okay. So, we are looking for shortest path. So, first let us define what do you mean by path between two vertex. So, let us consider a graph. This is a directed graph. We have given a directed graph or diagraph which is v comma e, and we have a edge weight on the edges. So, each edge is having some weight. So, this is the weight function. And now, if we have a path, path means we start with a vertex v 1 and then we have to reach to a vertex v k, and we must follow the edges. So, these are the v 2, v 3, these are the intermediate vertices which we visit, and these are the edges we follow. So, this is a directed graph. So, edges have a direction. So, we follow the direction, we will reach v 1 to v k. So, that is a path. Basically, we take an example. So, this is our v 1, and suppose we have a edge like this which is reaching to v k. So, this is a path from v 1 to v k. Now, what do we mean by weight of this path? So, weight of a path is basically sum of the weight of all the edges on the path. So, sum of the weights of all the edges on the path. So, for this path, general path, we have weight of w. So, I is equal to 1 to k minus 1. So, weight of if we put I is equal to 1, so this is this edge, weight of this edge, then weight of this edge. So, basically it is the sum of the weight of all the edges in the path. So, that is the weight of the path. For example, for this path, this is a p, if we represent this path. Now, what is the weight of this path? Weight is basically sum of the weights of the edges in this path. So, what is the sum of the weights of the edges? So, 4 minus 2 minus 5 plus 1. So, this will give us minus 2. So, this is the weight of this path, which is the sum of the edges on the path. So, this is a path and weight of the path. Okay. So, now we define what do we mean by shortest path between two vertices u and v. So, suppose we have two vertices u and v, we have two vertices u and we have another vertex v in the graph, any two vertex. Okay. Now, there could be many paths from u to v, or there may not be any path, physical path from u to v, that is also possible. Suppose there are few paths from u to v. So, this is a p 1, one path, and this is p 1, and we have another path, say p 2, and we have another path p 3, like this. So, we have say a few paths from u to v. Okay. Now, we can calculate the weight of each path, weight of p 1, weight of p 2, weight of p 3, like this. So, basically we are looking for the path which is having the shortest weight, I mean which is having the least weight among all the paths from u to v. So, that is the weight of the weight of the shortest path weight between from u to v. So, that we denote by delta u comma v. So, delta u comma v is basically the weight of the shortest path from u to v. So, that is the minimum of the path weight of all the for the all path from u to v. So, we consider all path from u to v and we calculate their weights. Among these, whichever is the minimum weight, that is basically delta u v, and that path is basically our shortest path from u to v. And if there is no shortest path from u to v, then we define this by infinity. So, infinity means there is no shortest path exists from. There may not be some, I mean, yeah. So, there may not be any physical path from u to v, that is also possible. So, in that case we define the delta of u v to be infinity to indicate that there is no shortest path from u to v. Okay. So, this is the definition of a shortest path weight delta. We use this delta notation to denote the weight of the shortest path from u to v, and this is the minimum of all the path weight, minimum among all the path weight from u to v, and we take the minimum one as a shortest path, and the weight of that shortest path is basically delta. Okay. So, now the question is we have to find this shortest path. So, we want to see whether we can use the dynamic programming technique, which we know 2 lecture before. We have discussed DP technique. So, there we have discussed there are 2 hallmarks for the DP dynamic programming technique. One hallmark works optimal substructure problem. So, that means if we have given the solution of the whole problem, that should contain the solution of the sub problems. So, that was the optimal substructure. So, do you have such optimal substructure property in this shortest path problem? Yes. The theorem is telling a shortest path, a subpath of a shortest path is also a shortest path. So, suppose we have given a shortest path between 2 vertex u and v. Now, if we consider a subpath, say this is x y. So, this is a subpath. So, this will be also shortest path between x and y. Okay. So, this is basically if this is u and this is v, if we have given a shortest path from u to v, and if we consider a subpath x and y. So, this is a subpath between x and y. So, now our claim is this subpath between x and y, and which is a subpath of this shortest path between u to v. Our claim is this is a shortest path from x to y. So, how to prove that? We will prove it by contradiction. Suppose it is not a shortest path from x to y. So, that means there will be another path from x to y which is whose weight is less than this weight of this path. So, that is the new path, this path weight is less than this path. Now, if we take a path from u to v like this, we go from u to x, then we take this new path, and then we go from y to v. So, that what is the weight of that path? Weight of that path will be less than weight of this path, because the weight of this path is less than weight of this path. So, the weight of this new path is less than weight of this path, which contradict the fact that this is a shortest path from u to v. So, that is the proof. So, if we have a every subpath of a shortest path is a shortest path between the intermediate vertices. So, this property we will use. So, this is called optimal substructure property. Okay. Now, we will use another property which is called triangular inequality of the shortest path. So, this is telling given any 3 vertex in the graph x, u, v and x. Now, the shortest path between u and v is less than equal to shortest path of u to x and shortest path of x to v. So, then how to prove this? So, let us prove this by this figure, it will be clear from this picture. So, shortest path from u to v, this is the say delta of u v we know, and we take this path shortest path from u to x, and this is the shortest path from x to v. Okay. Now, what this is a path from, so we let us consider this path. We take u to x, we take this shortest path, and then from x to v we take this shortest path. So, this is basically a path from u to v, and what is the weight of this path? Weight of this path is delta of u x plus delta of x v, and the shortest path is must be less than equal to weight of the all other paths. So, this is one path. So, that means delta of u v must be less than equal to this path. So, that is the proof. So, delta of u v must be less than equal to delta of u comma x plus delta of x comma v. So, this is the proof of this theorem. So, this theorem is called triangular inequality. We will use this theorem for our algorithm. Okay. Now, the question is, suppose they are given 2 vertex u v, if there are physical path from U to V, will there always exist a shortest path? So, that is the question. The answer is no, because if in that path, if there is a negative cycle, then shortest path may not exist. For example, this is 2 vertex UV, suppose in this path we have a negative cycle, this is a negative cycle in the path. So, in this case shortest path won't exist. Why? Because if we say shortest path means minimum weight, so there will be no path which is less than that. Now, if we claim this is our shortest path, then what we will do? We will go from here to here, then we will hop one more time to reduce, because this is the negative weight cycle. So, this weight is negative. So, we will hop one more to reduce that weight, and then from there we will go again to V. So, this will reduce the weight of the path which are claiming to be shortest path. So, it will never converge. So, if there is a negative cycle in the path, then the shortest path may not exist in that case. So, we have to be careful with the negative cycle. So, negative cycle in the path means there will be no shortest path. Okay. So, that we have to be careful. So, now let us come to the algorithm. So, the first algorithm we will discuss is the Dijkstra's algorithm. So, let us discuss the Dijkstra's algorithm. Okay. So, this is to find the single source shortest path. So, what do you mean by single source shortest path? So, we have given a graph G and we have given a vertex, which is a vertex from V. So, that is also part of the input, and we have to find the delta of S comma V for all V. So, this delta of small s comma V. So, that is called single source. So, we have given the vertex, one vertex is given. So, this is G, which is a graph, directed graph. So, this is V comma E, this is the vertex shape, this is the S shape, and we have W, the weight function, which is the weight from each edges having some associated with the weight. So, that is the weight function, and we have given a S, small s, which is a vertex given, that is also input. So, this 3 is the input. So, S is the any vertex could be a input. So, basically we have to find the shortest path from S to all other vertices. So, that is called single source shortest path. Source is given. So, we have given the vertex S, and from that vertex we need to find the delta of S comma V. So, for all V, and here this Dijkstra's algorithm cannot handle the negative cycle. So, for that we want to avoid the negative cycle. So, for that what we do? We just take all the edge weight to be non-negative in order to avoid the negative cycle. If our edge weight are non-negative, then there will be no negative cycle. So, that is why this weight function is from E to R, I mean non-negative, there will be no negative weight in the edges. So, that will guarantee that there will be no negative cycle, because negative cycle our algorithm cannot, Dijkstra's algorithm cannot handle the negative cycle. Okay. So, this is the problem. Problem is we have given a graph V comma E, which is a directed graph, and we have associated with a weight function on each of the edges, and which will not create any negative cycle. So, that is why we are assuming all the weight functions are non-negative for all the edges, and we are having a source S, which is a vertex basically, and we have to find the delta of S comma V, that is the output. So, that is for all other vertex we need to get the shortest path from S to other vertices. So, that is the problem. So, here we will apply the greedy technique for solving this problem. So, that is our Dijkstra's algorithm. So, the idea is to what to do, we maintain a set S, capital S of the vertices whose shortest path distance from small s are known. Okay. So, S is a vertex, we will maintain a set S, this is our set S, capital S, for which, so what is the first candidate for capital S? So, small s, because if there is no negative cycle, then what is the best way to go from S to S? It will be remain at S. So, that means delta of S comma S is 0. So, that is the shortest path, weight of the shortest path from S comma S. So, we start with the smallest, okay, and slowly every time we at each step we will add a vertex S from the remaining vertex. Those are basically V minus S or S capital S complement V minus S. We add a vertex, every time we add a vertex, say U, whose distance estimate from this S smallest is minimum. So, that is the greedy choice. So, we consider all the vertices over here and we have a distance estimate. So, we basically we key all the vertices by the distance estimate of that vertex from S to that vertex. I mean, what is the basically what is the path weight from S to that vertex. So, that is called distance estimate. So, we keyed all the vertex. So, initially we put all the vertex into the priority queue and we do the initialization step, and then slowly we update this vertex whenever it will be captured in S. So, we will come to the code in the next slide. So, idea is, so at each step we add a vertex from this V minus capital S whose distance estimate from S is minimum. So, that is the greedy choice, that is the local optimal, and it will be the global optimal. So, we have to prove that. So, once we are adding that vertex which is having the minimum distance estimate, so we have many vertices over here. So, we capture the vertex whose distance estimate from S to that vertex is minimum. So, that is the key of each vertex, we can say. We key the each vertex by the distance estimate of that vertex from the source vertex. So, that we will do. And once we capture a vertex from whose distance estimate is minimum, we capture the vertex in S. So, once we capture the vertex in S, so this U will be coming to S now. Then we consider all the vertices which are adjacent to this vertex S, and these are say V vertex, or if this is V, anyway. So, this is say V and this is say X vertex. Okay. Now, these are the all vertices which are adjacent in the adjacency list of V, which is just added into S, whose distance estimate was minimum. Okay. Now, for these vertices we have to we have a path, we go from S to this vertex and then we can take the direct edge. So, this distance estimate from S to this plus this weight of this. So, if the distance estimate what S was having is greater than the new distance this weight of this new path, then we must update that. So, that we will do. We update the for each of these vertices which are adjacency vertex of this new vertex which we have added to S, we update the distance estimate of the vertex of the all adjacency vertex of S. So, that is the idea. So, we will come to the code and then it will be more clear. So, this is the pseudocode for this Dijkstra's algorithm. This is a greedy algorithm. So, what we are doing, this is the initialization step. We initialize the key value of each vertex like this. So, we know the distance estimate from S to S is 0 because there is no negative cycle. So, the best way to be S to S is to remain S in S. So, that is the key value of S to be 0, and for all other vertex we put it to be infinity, because that is basically we have an explore yet. So, we do not know whether there is a shortest path from S to that V. So, that is why we keep this to be infinity. So, this is the initialization step, and we initialize that capital S by empty, because and we put everything, all the vertices are in the priority queue, which is Q. So, we are putting everything in Q, and then we will have this while loop, and this loop will run V times until the queue is empty. So, initially everything is in Q. So, there are V many vertices. So, then this will run order of V times. Okay. So, now we extract the minimum. So, whichever the minimum key value in Q. So, the first candidate, first U will be the S, because the key value of S is 0, others are infinity. So, 0 is the minimum. So, it will be extracted from this Q, and once extracted means it will be deleted from Q and it will be added in S. So, S is now first candidate of S is capital S is small s. Okay. And once we are adding a node in capital S, what we are doing? We are checking the adjacency vertex of, so this is our S and this is our U, which is the new vertex is added in this, which is the greedy choice. That means we are taking the whose distance estimate is minimum from this source vertex. Now we check all the vertices which are adjacent to this U. Okay. So, this is one such vertex V. Now, we have S over here, initially S is V, small s. Now, this is a path from S to U and we have a direct edge W of U comma V. So, this is a path from U to V. Now, weight of this path is basically du, which is the distance estimate from S to U and which is added in S, and later stage we will see whenever a vertex is added in S, capital S, for that vertex we are done. That means for that vertex, which is the key value, is basically the delta of S comma V. So, this we have to prove, delta of S comma V. So, whenever a vertex is adding in the capital S, for that vertex we are done. So, for that vertex we got the shortest path from S to that vertex. So, this is the shortest path. So, the delta of, so this du is the weight of the shortest path from S to U, and then we have a direct direct edge, that is W of U comma V. So, then this is a path from S to V. Now, V was having another path, or maybe it was initialized by infinity. So, that path was dV, that is the key value of V. Now, we have a new path from S to V. Now, if this path is better, that means if this weight of this path is less than dV, then we must change it, we must keep this path in our record. So, we must update that, and this is called, this step is called relaxation step. We must change the key value of V by this weight of this new path. So, that is basically du plus this, and this step is called relaxation. We are relaxing this edge. This is the relaxation step. Okay. This is only we will do if the new path, that is to V, is better than the earlier path. This is the dV was the distance estimate of the earlier path. That means there was a path from S to V whose weight was dV, or maybe it was infinity which we initialize. But if we have a better path, that is the new path du plus WUV, then we must keep this path in our record. So, then we update that key value of V by this one. So, that is the that is by this step, and this step is called relaxation step. Okay. And this is basically the decrease key operation. We have to go to that particular position and we have to change this key value. So, that is the decrease key operation, and that time will depend on the which data structure we are going to use for that. So, this is the algorithm, and this will run for how many times? This will run for until Q is empty. So, that is the idea. So, idea is we maintain a set capital S of the vertices whose distance estimate from the smallest are known. So, initially smallest will be in capital S, because distance estimate of smallest is known from S, because that is 0. Okay. And each step we add one vertex from this V minus S, that is from the priority Q, whose distance estimate is minimum, distance estimate from S is minimum, and this du basically this du d of V or du basically gives us the distance estimate, that is the key value of this vertices which are in the priority Q, key value, and these du's are basically the distance estimate of the vertex V from S to V, that distance estimate. Okay. So, that is the idea. So, let us take a quick example. Okay. So, now this is the given graph, this is a directed graph, and we have the vertices. So, this is the input and we have the edge weight, and we are not allowing any negative weight edge because to avoid the negative cycle. Okay. So, now we should have a source vertex to start with, that is also part of the input. Suppose this is the source vertex we are going to start. So, this is, and we initially we put everything into the queue, priority queue with the key value. For source vertex this is 0, for other vertex it is infinity, and we initialize this capital S by empty because we are just starting. Okay. Now, slowly we add this one vertex in S at each step by the greedy way, that means which vertex we are going to add, whose destination, because these are key values, this is our DV basically, the key value of these vertices, and these are basically the distance estimate from the source vertex. So, initially nothing is explored, that is why you are putting infinity, and initially this distance estimate from S to S is 0, that is why it is 0. Okay. Now, first step, if we extract the minimum, because this is the extract mean. So, this is the loop, we are coming into this loop, we check whether Q is empty or not. Q is not empty because all the vertices are there. Now, we extract the minimum. So, if we extract the minimum, who will be the minimum? So, minimum is A. So, A will be extracted. So, we extract A from Q. So, that means it will be deleted from Q, and it will be, we are adding it to S, capital S. Okay. And now, this is our U. Now, we need to check the all the adjacency vertex of this U. So, if you recall this. So, now this is our U, and now we need to check all the adjacency vertex of U, and we need to check this relaxation step. I mean, for those that V, if we have a better path now, we must update that. So, that is the idea. So, on that idea, okay. So, this is our V say, because these two vertices are in the adjacency list of this vertex. So, now it is having a distance estimate infinity. Now, we have a path, we S to S with 0 plus 10. So, 10 is the path length from S to this vertex. Okay. Now, 10 is better than infinity, so we must update that. So, we must relax this edge. So, this will change to 10. Similarly, this will change to 3. So, that is we are done. So, this is changed to 3, key value of B and key value of C will be changed to, key value of B will change to 10 and key value of C will be changed to 3, and this will be infinity remain. Okay. Now again we will check whether Q is empty or not. Q is not empty, we have 4 more vertices to go. Then we take the next, extract the next minimum. So, next minimum is basically from Q. So, these are the all vertices in Q, these two are infinity, the key value, and these two are, so 3 is the minimum. So, the C will be extracted. So, C will be our new U. So, C will be extracted from this Q and C will be added in S. Okay. Now, this is our C, new U, and this is the this is the weight of the shortest path from S to this node. This is basically our key value of C. Okay. Now, this is our U. Now, we have to check all the V's which are adjacency to this. So, this is our one V. So, this was having a distance estimate infinity. Now, we have a path from S to C, we can go by 3 weight plus this direct edge 2. So, 5 is better than 3. So, we must 5 is better than infinity. So, we must relax this. So, this will change to 5. Similarly, this will change to 3 plus 8. So, 11. And we can check this one also. This was having 10. That means, we are having a path from S to this with a cost 10. I mean, with a now we have a new path. We can go from S to this vertex C with a cost 3, plus we can take the direct edge 4, 3 plus 4 7, which is better than 10. So, we must relax this edge. We must update that new path. So, that will do, and so that will do. So, this all these 3 vertices are relaxed. I mean, we update their key values. So, that is the by decrease key operation. So, depending on which data structure we will use, we will go to that position. If it is array, we can directly go there and we can change the value. So, we will come to that in implementation. So, all this value will be changed. B, key value of B is 7 now, key value of D is 11, key value of E is also changed to 5. Okay. Now, this is our the B, D, E is now in our priority queue, and AC is already added to S. Now, if we next time, now if we check whether priority queue is empty, it is not. So, we have to get the next minimum, we have to extract the next minimum is 5, basically E. So, this is our next minimum. So, this is our new U. So, this is our U vertex, which is extracted from the Q and which is added in S. So, this is the new vertex added in S. Now, what is the what are the, so once it is added in S, then the degree of that vertex, degree means the key value of that vertex is basically the delta of S comma U. So, that is the, that we need to prove. Once we added a vertex in S, for that vertex we are done. So, for this so this is basically delta of S comma U, delta of S comma U. Once it is added in S, we are done. So, that degree, that key value is basically the delta of S comma U. So, that will prove in the correctness of this algorithm. Okay. Now, so this is the this is our we have a path, we have a shortest path from S to this vertex U with a cost 5, and this is our delta of S comma U. Now, we have to check what are the vertices are adjacency to this. So, this is the vertex adjacent to this. So, this is our V. Now, for this vertex we are having a path which is 11, whose cost is 11. Now, we have a new path. We can go from S to this vertex with a cost 5 plus direct edge 9. So, 14. 14 is not better than 11. So, we are not going to do the relaxation of this. So, it will unchanged. So, now will be the next minimum. Next minimum is the so next minimum is 7. So, 7 is our next U. Okay. Now, once it is added in, so B basically 7 means this B. So, once B is added in S, so for that U we are done. So, this is basically the 7 is basically the delta of S comma U. So, we have a path from here. So, we can track the path if we want to report the path other than these deltas. So, this is our U now, which is added in S, capital S. Now, we need to check who are the vertices adjacent to this. Now, this is the vertex adjacent to this V. Okay. Now, it was having a path 11 whose cost is 11. So, we have having a path from S to this, cost is 11. Now, we have a new path. We can go from S to this vertex U with a cost 7, and then from there we can take this direct edge which is cost 2. So, 7 plus 2 is 9, which is better than 11. So, this path is better. So, we must keep this path in our record. So, we must do this relaxation. So, we update this key value to 9. So, this is the decrease key we must do. So, this will change to 9. And then who are the vertex adjacent to this? So, this is vertex. So, this we can check, this is 7 plus 1 so 8, but 3 is not, but it is already a cross check because 3 is already in S. So, for S we do not need to worry about. Whenever a vertex is already added in S, for that we are done. But here is you can have a cross check. So, 7 plus 1 8, 8 is not better than 3. So, we are having a better path to reach to this node from S. So, we will not do relaxation on this. Okay. So, that is we only change this. Now, who is the next minimum? We have only one vertex remaining in Q. So, that is 9, I mean the D. So, that will be extracted and that will be added in S. And we can check for this vertex U. We can check this is the only vertex which is the adjacency list. This is 5 and this path is say 9 plus 7, which is not. So, that is also a cross check that we are, whenever a vertex is added in S, we are done for that. Okay. So, then finally, so Q is empty and we stop, because the outer loop we stop when Q became empty. So, this is the execution of the Dijkstra's algorithm. which we have discussed, and ultimately after the execution, after this Q is exhaust, then this will give us the weight of the deltas, basically weight of the shortest path from S to all other vertices. And if we have to get the, if we have to, these are the deltas. So, that means shortest path from A to E is 5. So, delta of A comma E is 5, A is our S. Now, that is our delta. Now, how to, if we have to get the shortest path, then we have to keep track of that whichever how it was relaxed. We have to keep track of that path in order to report the shortest path. Okay. So, but this is basically our deltas, and we got this. Now, we have to do the correctness of this Dijkstra's algorithm. Okay. So, correctness of this theorem we will prove in two parts. Part 1 is basically we want to show that in the so initial condition of the key value is like this. So, we initialize the key value of the starting source vertex as 0 and all other vertex as infinity. Okay. And this is the invariant we want throughout the executions. This key value of a vertex must be greater than equal to delta of S comma V. So, that is the weight of the shortest path from S to the vertex V, and this is the key value of the vertex V. So, this key value throughout it is greater than equal to the delta of S comma V, and when it will be equal once the vertex is going to add in S. Once the vertex U is added in S, for that vertex we are done. For that vertex equality will occur. For that vertex key value of U is equal to delta of S comma U. So, that part we will prove in part 2. So, part 1 is just this theorem, this lemma is telling that d of V is greater than equal to delta of S comma V for all the vertex, and this invariant maintained in over any sequence of relaxation step. So, how to prove this? So, we will prove this by a contradiction. Suppose not, suppose this is not true. So, so there will be a vertex, first vertex which is violating this. So, that means for that vertex key value will be less than. So, initial condition is infinity, infinity is always greater than any other minimum, any other value, real value. So, it is true for, but and for S is also it is true, because that is the, for S we know that is the delta of S comma S. Okay. Now, suppose the V is the first vertex for which the key value of V is less than, strictly less than the delta of S comma V. V is the first vertex. Okay. And let U be the vertex that cause dV to change to dV equal to du plus WUV. So, so the V, because it has to change from infinity to some numbers, otherwise infinity is always greater than some real value. So, and that suppose U is the vertex that cause change of this key value of V, and this is the change. Okay. Now, what is dV? We assume that this, we reach to a contradiction. We assume that dV is less than delta of S comma V. Now, we will use the triangular inequality. So, we are at S, we want to go to V. So, triangular inequality is telling us delta of S comma V is less than equal to delta of S comma U plus delta of U comma V. Okay. And UV is the direct edge, because that is the change V is going to, I mean U is already in S and V is the first vertex for which it is violating. So, and this is basically direct edge UV, and this is delta of S comma V. So, any specific path is less than specific path, this is the direct edge which is less than the specific path. Now, this is nothing but less than equal to du plus WUV, because this is U is not violating it. So, only V is the first vertex which is violating. So, this must be less than equal to du, because this is true for the vertex U, because V is the first vertex which is violating. So, that is the contradiction, because if this is dV is less than this value, then why we will going to do the relaxation? So, that is the contradiction, because the V is going to the U vertex, U is the vertex which caused dV change to this relaxation. So, that is the contradiction. So, throughout the relaxation step or throughout the algorithm, we have this invariant. So, key value of a vertex is greater than equal to delta of S comma V, and in the next theorem we will show the key value of a vertex will be equal to delta of S comma V whenever we are adding that vertex to the capital S. Okay. So, that part is this part. So, this part is telling Dijkstra's algorithm terminates with. So, when we end up with the algorithm, then it will give us the degree of the vertex, I mean the key value of the vertex is basically delta of S comma V. So, this is the correctness. So, how to prove this? So, to prove this, it is sufficient to show that dV is equal to delta of S comma V for every vertex when V is added to S, capital S. Okay. And suppose U is the first vertex added to capital S for which this is not true. So, we are going to capture this vertex U and which is going to be added in S, because this is the minimum, this degree of, I mean the degree means the key value of U is the minimum. So, in our algorithm we are going to choose this vertex as the next vertex to be added in S, and suppose this is the first vertex which are going to be added, which added in S, for which this is not true, du is not equal to delta of S comma U, okay, and we will reach to a contradiction. And suppose then then there will be vertex x in the S and there will be direct H which is to y is outside S, capital S, okay, y be the first vertex in V minus S along a shortest path from S to U. So, this shortest path, and x is a predecessor, x is in capital S and this is a direct H. So, W of S comma y. Okay. So, now U is the first vertex which is violating this claim that du is not equal to S comma U. So, that means for x it is true. So, this is sort of by induction you can say, because for S this is true, because for S du is 0, ds is 0 and that is same as delta of S comma S. Now, if we assume this is true for this, we have to prove this is true for next vertex. So, that is by contradiction. So, now ds is equal to delta of S comma S, because V is the x is the U is the first vertex which is violating, but so for x it will be true. So, degree key value of x is delta of S comma S. Since the path of the this is the optimal substructure, the subpath of the shortest path at the shortest path, it follows that dy was set to delta of S comma x plus W of x comma y, because this is the direct edge. So, this will be the basically dy is nothing but delta of S comma y when x was relaxed after the x is added to S, because this is the direct edge and there is no negative cycle. So, that is the shortest path and this is the shortest path. So, this will give us the shortest path from S to y, and that is basically dy. Okay. Consequently, dy is basically, we know this is just now S comma y we have seen. Now, this is must be less than equal to delta of S comma u, and which is less than du, but du is less than dy, the key value of u must be less than du. That is why this is going to be added before y, because this is the greedy algorithm we are using. So, we will take the whose shortest, we will add a vertex whose shortest distance estimate from S to that vertex is minimum. So, dy must be less than equal to du must be less than dy by your choice of u, and hence dy is equal to delta of S comma y, which is delta of S comma u, which is du, which is a contradiction, because this should not be true, which is we have assumed. So, that is the contradiction. So, that means what? That means at the end of the, whenever a vertex is going to add in S, for that vertex we are done. For that vertex, the key value of that vertex is basically delta of S comma that vertex. So, that is the correctness of this theorem. Now, let us quickly analyze the algorithm. What is the time complexity for algorithm? So, initial part will take order of v times, v cardinality of v. Initial part is there that we are putting the key value of s is 0, key value of other vertices. So, that part will take order of v times. Now, we come to this loop. So, this is a while loop of the this is the priority queue, this of size is order of v, and here we have a here we are doing operation extract mean. So, this will depend on which data structure we are using, the time complexity. So, the v times we are doing extract mean, and this is the decrease key operation, this relaxation. So, this decrease key operation how many times we are doing? We are doing this is summation of degree of u basically, and this sum is over u belongs to v. This is for all such u we are doing this. So, that is basically from handshaking lemma, that is order of e. So, order of e times we are doing this decrease key. So, total time complexity is order of v times we are doing this extract mean, this is the time to take the extract mean, and order of e time decrease key. So, this time complexity is same as the Prim's time complexity which we have discussed in the last lecture. So, this is the details. If we are using array, then the extract mean will take the, we need to find the minimum in the array. So, the key values whose key value is minimum. So, that will take us this time, but decrease key we can go to that particular position, we change the value. So, that will take constant time, and this is order of v square, and this is basically by binary heap, mean heap. So, this will be logarithm time because we have to do the mean heap pi after taking the minimum from the root, and then we have to do the even decrease key also we have to do the log of this. So, again mean heap pi at that point. So, this will cost at this time. So, this is the time complexity of this. Okay. So, now let us discuss the another algorithm which is called Bell-Manford algorithm, which is more general algorithm in the sense that in the Dijkstra's last algorithm we have restrict ourselves to the non-negative edges. So, edge weight are non-negative to avoid the negative cycle, but negative cycle could be there because graph is any graph or any directed graph. So, we may have negative cycle. So, we need to have an algorithm which can handle the negative cycle, and we know if there is a negative cycle in the path, there will not be any shortest path from u to v because we can hop there as many times as we want. So, that will never converge. So, Bell-Manford algorithm, it will find the all shortest path from S to vertices, or it will report that there is a negative cycle in the path. So, that is the little more general algorithm than the Dijkstra's. So, it is also a single source shortest path. So, we have input a graph v comma e, and we have the edge weight. So, we have w also. So, w is e to r over here. So, earlier it was r plus, but here we can allow we can handle the negative cycle. So, we are allowing the negative weight edges also. So, there is no restriction on the non-negativity, and we have a source vertex S, which is any vertex could be a source, that is also part of the input. Okay. And we have to find the delta of S comma v for shortest path weight for all other vertices from S including S, or we have to report that there is a negative cycle. So, that is why shortest path will not exist. So, that is the thing. So, let us this is the pseudocode for Bell-Manford algorithm. Now, here initialization step is very much similar to the Dijkstra's. Key value of S we are putting 0, and other key value of the other vertex we are putting infinity, because we do not know whether the shortest path will exist or not. So, initializing by infinity, that is why we define delta of S comma, if there is no shortest path between two vertex, we define delta value to be infinity. That delta means the weight of the shortest path from u to v. Delta of u to v is infinity if there is no shortest path from u to v. Anyway, this is the initialization step, which is same as the Dijkstra's algorithm. Now, here we have a for loop in I, and this loop size is order of v. Okay. And inside the loop what we are doing? We are doing lots of relaxation. What we are doing? We are taking each edge. So, suppose there are order of E size edge. So, cardinality of E. So, we take every edge and we are doing the relaxation if it is possible. So, we are checking whether the degree of, so we are just taking a edge. So, this is a vertex U and this is vertex V. So, this is a direct edge and this is W of U V, weight of this edge. Okay. And we have a dV, which is basically key value of V, which is the distance estimate from the shortest path from S to V. Okay. Now, we have a path, we can go from S to U with a cos du, plus we can take this WUV. So, this is the new path from S to V. This is one path. Now, if this path is better than the earlier path, so if this path is less than dV, then we must update this path. So, that is what relaxation step is. So, we must relax this vertex, we must change the key value of this vertex by this new weight. Okay. So, this is a relaxation and we will do it for every edge inside the loop, every edge for every I. So, for I is equal to 1, we take every edge. If there are say m number of edge, we do it for every edge, we do this relaxation if possible. Then for I is equal to 2, again m times, I is equal to 3, again m times. So, lots of relaxation is going on. So, we do how many times? We do order of V into E times. This size is order of E, cardinality of E, and this size is order of V. So, order of V into E times we are doing this relaxation. So, lots of relaxation we are doing. Now, even after doing lots of relaxation, we do check whether there is a negative cycle or not. So, that check is this. Finally, doing lots of relaxation, we will just have a last check. So, if there is no negative cycle, so by this time it should converge. By this time this dV, all the dVs will be converged to delta of S comma V. It will not converge if there is a negative cycle, and that check will be done just by one shot. Again we check for every vertex, every edge, we take a edge and then we check whether further relaxation is possible or not. If that is possible, then there has to be a negative cycle, because we have done enough relaxation over here and that is sufficient. We will prove that. We will have a correctness of this theorem, we will prove why it is order of V times, why the order of V times is sufficient for this convergent. So, if there is a negative cycle, it will never converge, then in that case it will keep on updating, the relaxation will keep on going on. So, that check will be done by this last step. This last step is basically we check for each edges, and if we can do further relax this V, then we report there is a negative cycle, because it will never converge. So, this is the pseudo code. We will take a quick example, and at the end it will be delta of S comma V, or it will report a negative cycle. And what is the time complexity? Time complexity is V into E. Let us take a quick example. Suppose this is the given graph and we need to run the Bellman-Ford algorithm on this graph. Here we are allowing the negative weight because we can handle the negative cycle. So, these are the negative weights. So, it is more general algorithm than this. Now, than the Bellman-Ford. Now, these are the vertices we have. So, what we are doing? We are initializing the key value of the vertices as this, that is initialization is same as the Bellman-Ford. Now, we have to do for I is equal to, we have a outer loop in I is equal to 1 to V minus 1 time, order of V minus 1 time. We need to do this loop, and this loop size is order of E. For every edge we need to check this. So, that we are going to do. So, for every edge we need to do. So, we can do some edge numbering. So, say this is for number 1 edge. So, we check this. So, this is U, this is V. So, this is infinity, this is also infinity, no relaxation is possible. This is edge number 1. So, then suppose this is our edge number 2. Then again we check, both are infinity, no relaxation is possible. Then suppose this is edge number 3, same, these two are infinity, no relaxation is possible. Now, here there will be change, because this is U, this is V, this was infinity. Now, we have a better path. So, this is 0 plus minus 1 minus 1. So, this will change to minus 1. Now, the next vertex is next edge is this one. So, this will also change to 4 and the next edge is this one. So, this was infinity, this is 4. So, so this is better because this is no change, no relaxation, and this is this one. So, this was 4. Now, we have a path like this. So, this is minus 1 plus 3. So, 2. So, this will change 4, this was 4, this is now 2. So, this will change. I think that is the this is the last number h. So, this is infinity, no change. So, this is done. This is for I is equal to 1. So, this loop is for, this is the initialization step, and this loop is for I is equal to 1. Now, we will do same thing for I is equal to 2. So, in that case, in that time we may not follow the same ordering of the edge, but we have to do it for all edge. So, we for simplicity you can follow the same ordering, but does not matter. Only thing you have to ensure that you are doing for all edge. So, again we will do this, we do. So, this was how much? So, this was E was infinity. Now, we have a path like this. So, this is minus 1 plus 2. So, 1. So, this will change to 1. So, this will change to 1. And now, what was the second this was the second edge. So, this was uv. So, this is will not change because this is infinity. So, no relaxation, this is So, this was infinity. Now, we have a path like minus 1 plus 2. So, it is 1. So, this will d will change to, the key value of d will change to 1. And then we have this no change because this is already now here also no change. So, same ordering of the edge we are doing, same numbering. You can have different ordering of the, only thing you have to do it, this was the last edge. So, what was the value over here? It was 1. Now, if we do this edge, it was 1. Now, if you do this edge, this is 1 and then minus 3, it will be minus 2. Minus 2 is better than 1. We must relax this. So, that is what we did. So, this is minus 2 d. So, d will change to minus 2. Then this is for I is equal to 2. And then you can check the next one, I is equal to 3, and we can just easily verify there will be no further changes there. Okay. So, we converge even by 2 step, I is equal to 1, 2. We can go up to v minus 1, v minus v is order of v is 5. So, 4. So, but before that it converge. So, this is there is no negative cycle, that means, because it is converged. So, this is Bell-Manford algorithm. Now, what is the correctness of this algorithm, why it is working? The correctness is we can prove by this theorem. If there is no negative weight cycle, then at the end of the algorithm, the Bell-Manford should give us the key value of each vertex is basically delta of s comma v. So, that is the theorem. We are going to prove this theorem. Let us take a vertex, arbitrary vertex v, a small v from capital V, any vertex, and let us take a shortest path from S to V, and it is visiting some of the vertices V1, V2, V3 like this, and P is the shortest path. Then we have delta of S comma Vi, take any arbitrary vertex, it should be equal to delta of S comma Vi minus 1 plus W of Vi minus 1 to Vi. Now, since there is no negative weight cycle, so S comma S is basically 0, that is the best thing we can do, we will be remain at S. So, that is basically degree of S, that is the initialization step. So, this is done for in the first initialization step. Okay. Now, for every step we will see, for every I we will see this will be slowly will be done, because this is an edge, we do not know the numbering, the ordering when this edge will come, but for I is equal to 1 this edge will come at some point of time. So, once this edge will come in the after first pass, then this will be done. Okay. So, this will be d of V1 will be delta of S comma V1, and once this is done, then in the I is equal to 2 this H numbering will come, and once this is done, then this will be done for I is equal to 2 pass. So, this way. So, that is why we have to go for maximum order of V times, because maximum there will be because there is no negative cycle. So, if there is a cycle, that will be positive cycle. So, positive cycle we can ignore, because this is a minimum shortest path. So, positive cycle we can ignore. So, this path is a simple path. So, there will be no repetition, because if there is a cycle, that will be positive cycle, we can ignore that. So, that is why we can hop this for v minus 1 time maximum, and every time, and if we are if we do the ordering like this is edge number 1, edge number 2, edge number 3, then it will be done by one shot, because once this will be done in that I is equal to 1, this edge will come first, this edge will come second, so it will be done. But anyway, that assumption we cannot make, because we do not know how the numbering will be done in the edge. So, that will depend on the implementation. So, that is the thing. So, if the dV fails to converge after even order of v times in that outer loop, then there exists a negative cycle. So, that is the okay. So, let us conclude this lecture. In this lecture, we have discussed the shortest path problem, given a graph, how we can find a what do we mean by shortest path between any two vertex u v, and when the shortest path exists, then the length of the weight of the shortest path, that is delta of a u comma v, and then we have discussed two algorithms to find the single source shortest paths. That means we have given a vertex, source vertex S. From that vertex, we have to find the delta of S comma v for all other vertex. So, we have discussed two algorithms, Dijkstra's algorithm and Bell-Manford algorithm. Thank you.